Hello friends, today I'm going to explain the match filters and why are they used and where are they used. And also I will gonna explain the proofs of the claim 1 and 2. So first of all my question will be what are match filters? So match filters are used in signal processing. So in signal processing uh, a template or a signal is correlated with an unknown signal to detect the presence of a template in an unknown signal. That's when the match filter is used. So this equivalent to convolving an unknown signal with a template. So my second question will be where are they used? Let's take an example of an ECG where we need to detect a heartbeat. So that's when a match filter is very useful so that we can detect a particular set of heartbeats from an ECG signal. So my third question will be how do they detect the signal? So let's take an example and explain the match filters and how are they used. So the example will be this ECG signal. This is an ECG signal. It's a random signal, and we need to detect the pulses like this from an ECG signal. So, um, in order to detect the pulses, we need to generate the impulse of every heartbeat, every pulse that we can see in an ECG that we need to find. So, what's the solution? We need to use a template and convolve the template with the original signal. That's when we can get the impulses of the heartbeat from an ECG. Let's explain this with a diagram. This is an ECG signal, random ECG signal, and this is the template. This will be convolute with the ECG signal, and hence we will get the impulses. So this template will pass onto an ECG, and hence will get an impulses in the final match filter. So when this template convolute with an ECG, when it detects a signal or a pulse like this, it will give impulse in the final response. So hence there are six pulses in an ECG, and hence we'll be getting six impulses in our final match filter. So how does this match filter does this matching process? Let's take an diagram to understand this. So this is our original ECG signal, and this is our template. Both the signals are convoluted with each other. That means they are both multiplied with each other. Hence, we'll get an this is the final product that can be found by the multiplication of both the signals. That is compared with a threshold, which gives a perfect value whether the convoluted signal is the one that we needed or that we need or not. If it's perfectly matches with the threshold, that means we have detected the impulse, and hence that will be the output of our response. Now let's take a signal and see how the matching process takes place in a match filter. So this is our original signal, and this is our template. So when a template is passed to an original signal, in this signal we'll get a 0, because when the slope of the template is negative and when the slope of the template is positive, both response are added up, and hence we get a final response of 0. When when the signal matches with the template, then the final response will be the square of both the square of the signal. Hence we will get an improved form of the signal. Hence it's a impulse. We can also say that it's a max response of a signal, as the negative slope will also be added to the positive slope. Hence we'll get the improved form or the max response of a signal. So this is basically the match filter. This is how the match filter detects a signal from any random or unknown signal. Now let's move on to the two claims that are very necessary in order to study match filters. So firstly, the claim 1, in which V of t is given as white noise, and SVW, the power spectrum, is given as constant. So we have three claims to prove. The system function h of w should be equal to k f of w e raised to minus j w t0. The second will be the impulse response should be h of t is equal to h inverse of t0 minus t, and the signal to noise ratio should be integration of the square root of integration of minus infinity to infinity fw square dw upon 2 pi s0. So firstly, we should know that what we already know. We know the formula of the signal to noise ratio, which is r square is equal to yf t0 whole square upon expectation of y of v whole square. So power of signal upon power of noise is the signal to noise ratio. We also know the Schwarz inequality, which also says that if the modulus of fx of gx dx whole square, then it is equal to it is less than or equal to fx whole square dx and gx square dx. Now let's move on to the proofs of the given claim. We know that r square is a ratio of square of power of signal upon power of noise, and we know the power of signal is nothing but 1 upon 2 pi integration of minus infinity to infinity y f of w e raised to jw t0 dw, and upon the expectation of y of v of t, which is nothing but power of noise. It is nothing but the area covered by the noise in a given spectrum, which is 1 upon 2 pi minus infinity to infinity svw dw. Now, according to the Schwarz equality, let's move on to the numerator and explain how it can be deducted into a reduced form. We know that this is the upper term, this. Now, we know that yf of w is nothing but hf into gf from our transfer function, as y of w is equal to multiplication of hf into f of w. So we have put that equation into this. Now, according to the Schwarz inequality, this term is nothing but less than h of w whole square into this term, this, which is nothing but this is equal to 1. Hence, which is nothing but this term can be reduced to only h of w whole square into f of w whole square. Hence, and also the limits we need to add, the integration of minus infinity to infinity. So this will mark as 1. Now, in order to find the denominator, the power of noise, we know that the denominator term is nothing but sv of w dw, integration of minus infinity to infinity. Hence, we know that the term sv of w is nothing but sv of w into sw of whole square dw, which can be reduced from this equation can be put into our previous equation number 1. Hence, putting both the equation of numerator as well as denominator into our final equation, equation 1, will get the whole term this. Hence, now we can cut 1 upon 2 pi and 1 upon 2 pi from the given equation, and also we can cut this term as well as this term from numerator as well as denominator. So hence we'll get the final result as r square is less than 1 upon 2 pi minus infinity to infinity this term upon sw. So this is nothing but our first given claim proof that signal to noise ratio is nothing but this. Now, according to the Schwarz inequality, we know that h of w is nothing but a constant into f of w e raised to j w t0. Hence, we can bring the inverse into the given function, and hence we can deduct the transfer function, the system function h of w as kf of w e raised to minus jw t0. Now let's move on to the claim 2. In claim 2, we need to prove the system function as this and the signal to noise ratio as this. So now we know that this is our original signal, this is our intermediate, this both are intermediate transfer function. Here the convolution take place, and here it's an intermediate transfer function, and this is our final output signal. We know from the claim 1 that h1 of w is nothing but kf1 inverse of w into e raised to minus jw t0. Now from our given transfer function, h of w is nothing but g of w into h1 of w. Now we know that h1 of w is nothing but k f1 inverse of w into e raised to minus jw t0. We can put that into a given equation, and hence we can deduct the final proof of the impulse system response of the given claim. We also need to deduct the signal to noise ratio. Now from claim 1, we know that the signal to noise ratio is nothing but this. We can put the S0 as 1 into the given equation, and hence also put f1 of w as fw whole square into gw whole square. We know that gw whole square is nothing but 1 upon svw. Hence we'll get the final signal to noise ratio of the given claim 2 as this. So hence this is my presentation on the match filter and the proofs of the claim 1 and claim 2. Thank you so much.